Thanks, Thijs, for the introduction. So my name is Sebastian. I'm working on fermionic sodium potassium at MPQ under the supervision of Emanuel Bloch. This is actually not us cooling our molecules and also not imaging our molecules. This was just for a photo stunt. So I don't think I have to go to this slide in very great detail. Why are we interested in these systems? We have long-range anisotropic interaction. We use fermions, and thereby, when we look at the many-body effects, we find a very rich phase diagram with exotic phases, such as p-wave superfluidity. And of course, bosonic systems also have been realized and looked at. Platforms for, in general, doing dipolar physics are, of course, like Rydberg atoms, magnetic atoms, or molecules. And while the first two have like their downsides either because they have a very short lifetime or rather weak dipoles, we hope with polar molecules we can sit kind of at the sweet spot with reasonable lifetimes, thanks to, in our case, microwave shielding, which Thijs and Jeremy introduced in the morning already in great detail. So I also can skip over this slide rather quickly. We, of course, have a dual feed waveguide antenna that we can use to generate near circular, but also very elliptical polarizations. And then you get this dip in the, do you see me? The dip in the intermolecular potential that you can then, by adding a dipole antenna with a pi polarized light, actually get completely rid of. So you can, if you want, completely cancel this, or you can also like really tune the interaction in the reaction. We were not the first to realize this. This is a technique that we adopted from the Will group in Colombia, and as we heard last week at DayMob, the one group in Hong Kong also implemented a similar scheme. Using this dual color microwave shielding, we now can routinely evaporate our sodium potassium down to something like 0.2 TeV, a little bit lower. Of course, it gets kind of challenging at this low densities to really accurately determine the temperature. So we hope that with reasonable technical upgrades, we can in the future actually create larger samples of molecules and thereby get lower temperatures and more fidelity in the temperature. My talk today, I actually want to show us our first results really with the system of quantum many-body effects. First of all, when we look at equilibrium physics, the first thing that you will see in the fermionic systems are deformations of the Fermi surface. So let me briefly revisit what happens when you use a fermion in a somewhat formed trap and let it expand in time of flight. So you actually see the momentum distribution, and this momentum distribution will be basically isotropic. You can use a cigar-shaped trap, it will be isotropic. You can use a pancake shape, or if you're feeling really fancy and want to use a unicorn-shaped trap, you also will see that the momentum distribution will be basically isotropic. This is different from molecules where you have where you can induce attraction along a certain direction, in our case using a microwave field or electric field. You'll actually find that for fermions, thanks to the interplay between kinetic interaction, which will lead to your sample actually trying to adopt this isotropic shape due to Pauli blocking, and the Fock exchange which will pull together your sample along the axis of attraction. You actually see that the Fermi surface will be deformed, and the cloud that you measure in time of flight, which is very important that you do with Feschbar molecules, so without interaction, you'll see that the cloud deforms in that way. This is actually opposite to classical dipoles or bosons, and I think we'll hear about that tomorrow, as I just learned in the coffee break. Once again, we are not the first people to actually look at these effects. Similar things have been observed with magnetic atoms already like some 10 years ago, where they actually rotated the magnetic field to realize different orientations of the cloud. For us, using our microwave setup, we can not only change the direction, but you can also change the relative strength of the interaction. So using the ellipticity of our sigma field, so of our circular microwave, and the second tuning knob, of course, is the Rabi frequency of the pi field. emitted by the dipole antenna. So how do we analyze this data? Let's say this is a cloud and you have to believe me here, is elliptical with about 8% deformation. You can actually nicely see this if you just rotate the image and then subtract the two images. You see this nice cloverleaf shape, and you see that the cloud actually has a deformation along this diagonal in this case. When we look at this for different temperatures and different ellipticities, we actually see this very nice feature that if we stay at 0 ellipticity, the deformation of the cloud is basically negligible, so the cloud stays round all the way. But once we go to a positive or negative ellipticity, the cloud deforms in opposite direction as expected, and the deformation grows as the temperature is lowered. So here you see we can reach basically down to something like 0.2 TF. The theory calculations here that you see in the shaded area behind are done by Wei Zhang from our collaborators in Beijing. We now can look at this deformation as a function of our two control parameters, the ellipticity and the Rabi frequency. And we actually see that we very nicely get a continuous change of deformation as we change the ellipticity. And basically the zero crossing, so where the two axes of the cloud are the same, happens where we, I'm very confused, the hydrodynamic regime here should be shaded in gray, but I barely don't see it, happens where the ellipticity is 0. So in a way, this is now a tool for us to actually understand where the 0 ellipticity is, because that's not necessarily not naturally very easy due to like the reflection of the microwave field in our setup. The discrepancy you see here between the theory curve in the solid line and our experimental data can be, at least to some part, be explained by a uncertainty in the number of collisions necessary for thermalization. So in the end, in these experiments, we always measure thermalization rate, and then to convert this to elastic scattering rate, you need to know how many events you actually need for the sample to thermalize. Similarly, we can do this for when we change the Rabi frequency, and we actually find here that the zero crossing happens at the point where the pi field perfectly cancels our sigma field, so we have no dipolar interaction. And this is also where the elastic scattering rate is the lowest. Now this was all equilibrium. What we recently have been doing, and I have to apologize because that was not in my abstract, because at the point of writing my abstract, we were not really at the point to really report these results, but this is basically data from the last 1 or 2 months, or maybe actually 1 or 2 weeks. We can actually look at what happens now with our system when we start perturb the trapping using our dipole trap. So you see this is basically our trap. It's a bit, in the end, as the trapping frequency are not that much different, but more like 70 to 45 hertz. And we start now shaking it in the XY plane. And then after a certain number of modulation periods, we stop it. And then we stop it at a slightly different angle. We get a different angle in the in situ image. So here it's important that we don't do time of flight, but we actually do in situ imaging. And we can do this all the way for, let's say, 8 points around one modulation period, fit this data and extract the amplitude, and do this for various frequencies. And we see that for certain frequencies, we get a very large amplitude. This basically is when the driving field or the driving frequency is in resonance with a certain mode of the ensemble. And here you see 2 example images at the very extreme. You really see how the cloud is rotated, one by 20 degrees and one by basically 0 degrees. How does is this excitation spectrum supposed to look like? Let's say we have 2 trapping frequencies, fx and fy. In the collisionist regime, we get the sum and the difference frequency. And in the hydrodynamic regime, we actually expect this crossover line. Of course, our sample is always like kind of in between the 2 regimes. So what we actually see, and this is now very, very preliminary data because in the meantime, we unfortunately ran into some vacuum problems, that as we increase the dipolar interaction, we first see only 2 peaks and then slowly see how I would say the one of the peaks starts melting away and we see a third peak appearing. This is, I really must say, very preliminary data, but to us, it at least looks very reminiscent of what people have been observing or theorizing about in the BEC to BCS crossover, where you also see as you go from the collisionless to the hydrodynamic regimes, you get a slight shift and in amplitude and position of these excitation peaks. And here we rely on the theory from, once again, our collaborators in Beijing, especially Wei Zhang and Tausche. But it was also kind of exciting to really do physics that our theorists did not immediately have an answer for. So it's kind of interesting stuff. With that, let me quickly summarize. I haven't shown you, but I think you have been convinced already by the talks this morning, and you will be even more convinced when Sebastian talks tomorrow, that using this dual color microwave shielding, we really get full 3D control over the intermolecular interactions. We have observed Fermi surface deformations in our system, and very recently we've been able to really measure variations of the scissor modes. And here the goal is really, as we go closer and closer to our long-term goal of reaching the P-wave superfluidity, we really expect these peaks to grow sharper and sharper and sharper. Of course, we wouldn't be Emmanuel's lab if we did not plan to put in a single-site imaging at some point. I think for the moment we still have a lot of things to do in bulk, so I hope we can stay in that regime until I finish my PhD at least. My colleagues, especially Christine, who's in the audience, will keep on the work. You probably will hear things in the direction of this quantum glass microscope in the future. Let me thank also our theory collaborators in Beijing, some of the former members who are also now in Beijing, or at our kind of sister experiment, lithium rubidium. There's another talk by my boss, Shinyu, tomorrow at after lunch, and 2 posters by Christina and Anwei, who will tell you a bit about what I just showed you, and also about really this new lithium rubidium machine that is currently being built up at MPQ. Thanks.
Yeah, thanks very much. Very exciting. Let's go to Zoe.
Really nice results. So on your last slide, you put a critical temperature for P-wave superfluidity. What kind of assumptions go in there? Is this weak coupling, BCS? Is this an effective potential? How do you get
So I must say I'm not expert on that. The 0.14 TF is the number that we always get from our theorists who do some, I guess they are coupled channel calculations for estimating this number. To be honest, the exact numerical value is a bit fishy, to me at least. So I can't tell you.
Beautiful results, awesome. I was wondering, or let me try to play devil's advocate. Is it a Fermi surface deformation, or do you see the same effect at 0.5 T Fermi, at 1 T Fermi? Does it have to do with being fermions, or would you see this also in a thermal cloud?
I must say, in a thermal cloud, I mean, you really see this here when we actually go. So we start basically at a thermal cloud, right, on the right hand side of our plot, and then this deformation only appears once we go colder and colder.
I missed that plot. That's beautiful.
Sorry.
Thank you. That answers that question. Can I ask you a second question? On the hydrodynamic peak emerging, you did mention it corresponds to BEC, BCS. Let's be careful, right? I mean,
yeah,
it just becomes hydrodynamic, right?
Exactly, it becomes hydrodynamic. Sorry. We were already worried about putting into this plot, and I think that shows why we probably should have been a bit more careful. This, of course, the plot I showed here on the right is a like very different system. So we don't expect the same behavior here. Yeah, I just want to say, like, we also see that as we go from hydrodynamic to collisionless, we see some, on one hand, like this change from 2 to 3 peaks, and also that the peaks kind of like melt away, get lower, change a bit in position.
Yeah.
So then it was more like a qualitative than really a
No,
quantitative.
it's very
number.
beautiful. You see the emergence of hydrodynamics. It's awesome.
Thanks for the nice talk. Can you say a bit more connected to this question about the time of flight? How you do it? Do you expand on the molecules and do you switch off something, or do you expand on the atoms also?
We have, in this case, we basically do in situ imaging. Of course, we only ever image atoms, so we never image the molecules. So we always, like, there's always some very small time of flight involved, because we first have to transfer from the ground state to the Fermi state, and then from the Fermi state to the individual atoms. But always when we do time of flight, we first switch from the ground state to the Fermi state. So we always do expansion in the Fermi state. So the Fermi molecules are basically not interacting, and that's why we claim to have basically ballistic expansion. Yeah. I must say, we upgrade our system, so we technically can also do syrup after some time of flight, but we haven't really used it at this point.
Okay, thank you.
Then I think we stop here. So thanks very much for a very exciting talk, and thanks to all of the speakers.